What would it feel like to stand at the edge of forever? To witness the one place in our universe where the laws of reality as we know them simply cease to apply. Imagine a boundary so absolute that once crossed, not even light itself can escape. This is the event horizon, the point of no return. For the next hour, you and I will travel together to this cosmic threshold, and in doing so, we might just find a profound sense of peace in the face of the ultimate unknown. Are you ready to take this journey with me? Before we can truly understand what an event horizon is, we need to begin with something far more fundamental. We need to talk about the very fabric of reality itself. You see, the universe is not simply empty space, with objects floating in it. Space and time are woven together into a single, dynamic entity that physicists call spacetime. Think of it as an invisible cosmic canvas upon which everything exists. Every star, every planet, every atom of your being rests upon this fabric, and more importantly, everything with mass causes this fabric to bend and curve in ways both subtle and profound. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression, a curve in the sheet around it. Now imagine rolling a marble nearby. The marble does not simply travel in a straight line. Instead, it curves toward the bowling ball, following the contours of the depression. This is essentially what gravity is. It is not a force pulling objects together as we once thought, but rather the natural motion of objects following the curves in spacetime created by mass. Everything in the universe, from the smallest grain of sand to the largest galaxy, warps the fabric of spacetime around it. Our sun, for instance, creates a gentle dip in spacetime, and our Earth follows that curve in its eternal orbit. The moon follows the curve created by Earth. This cosmic choreography plays out across the entire universe, from the smallest asteroids to the largest superclusters of galaxies. But what happens when you have an object so incredibly massive, so impossibly dense, that it does not just create a gentle dip in spacetime, but instead tears through it entirely? What happens when the curve becomes so steep that it essentially creates a one-way street in the fabric of reality itself? This is where our story truly begins. This is where we encounter gravity at its most extreme, most unforgiving state. When a truly massive star exhausts its nuclear fuel and collapses under its own weight, it can create something almost beyond comprehension. The matter compresses and compresses and compresses still further, until it occupies a space so small that the curvature of spacetime around it becomes infinite. The depression in our metaphorical rubber sheet becomes not just a dip, but a bottomless well. A cosmic trap from which nothing, absolutely nothing, can ever climb back out. And yet, despite the violence of its creation, there is something profoundly peaceful about contemplating this cosmic phenomenon. In a universe filled with chaos and constant change, a black hole represents something almost meditative in its absoluteness. Its boundary is not arbitrary or changeable. It is fundamental, written into the very mathematics of spacetime itself. There is a strange comfort in that certainty, in that unwavering law of nature. At the edge of a black hole, at the event horizon, the universe has drawn a line and said, beyond this, the rules change forever. Let us take a moment to simply breathe and consider what we are about to explore. We are embarking on a journey to a place where our everyday intuitions about time and space no longer apply. Where the faster you try to escape, the more trapped you become. Where time itself stretches and warps in ways that would seem like pure fantasy, except they are supported by our most rigorous mathematical theories and even by observation. As we prepare to approach the event horizon, let your mind relax and open to possibilities that exist beyond our terrestrial experience. You might be wondering, why study something so extreme, so far removed from our daily lives? The answer is both simple and profound. By understanding the most extreme environments in the universe, we come to understand the fundamental rules that govern all of reality, including the reality we experience here on Earth. The event horizon is not just a distant cosmic curiosity. It is a laboratory where the universe reveals its deepest secrets, where quantum mechanics and gravity meet in ways we are only beginning to understand. It is a reminder that our universe is stranger and more wonderful than we ever imagined. So take a deep breath. Relax your shoulders. Let go of the concerns of your day. For the next hour, you and I are cosmic travelers, voyagers on a journey to the very edge of what is possible in our universe. We will witness things that challenge our understanding of reality itself, and in doing so, we might just find a deeper appreciation for the incredible, improbable, beautiful universe we call home. Our journey to the event horizon begins now, and I promise you, you have never experienced anything quite like what awaits us. To truly appreciate the event horizon, we need to understand the cosmic events that create a black hole in the first place. These are not gentle processes. They are among the most violent, energetic events in the entire universe. It all begins with a star, but not just any star. We are talking about a massive star, one with at least 10 or 20 times the mass of our own sun. For millions or even billions of years, this stellar giant burns brightly, fusing hydrogen into helium in its core, creating the light and heat that would allow planets to exist in orbit around it. But nothing lasts forever, not even stars. Eventually, the hydrogen fuel in the core runs out. For a normal star like our Sun, this simply means a gentle expansion into a red giant, followed by a gradual cooling into a white dwarf. But for a truly massive star, the story is far more dramatic. When the hydrogen is exhausted, the core begins fusing helium into heavier elements. Then those heavier elements into even heavier ones. Carbon into oxygen. Oxygen into silicon. Silicon into iron. With each stage, the star buys itself a little more time, but with each stage, that time grows shorter and shorter. Finally, inevitably, the core of the star is pure iron. And here, the star faces a fundamental problem. Fusing iron does not release energy. It consumes energy. The fusion process that has sustained the star for its entire life can go no further. In an instant, on cosmic timescales at least, the outward pressure from fusion that has been holding the star up against its own gravity simply vanishes. Imagine a building where every support beam suddenly turns to dust. That is what happens to the star's core. Without warning, without ceremony, gravity wins, and the core begins to collapse. What happens next occurs in less than a second, but releases more energy than the star has produced in its entire lifetime. The core, no longer supported by fusion, collapses at nearly 1/4 the speed of light. In a fraction of a heartbeat, a core the size of Earth compresses into a ball just a few kilometers across. The density becomes so extreme that protons and electrons are squeezed together into neutrons. The collapse is so sudden, so violent, that it creates a shock wave that rebounds outward, tearing through the star's outer layers. This is a supernova, one of the most luminous events in the universe. For a few brief weeks, a single dying star can outshine an entire galaxy of hundreds of billions of stars. The explosion scatters the elements forged in the star's core across space, seeding the cosmos with the raw materials for future planets and, eventually, for life itself. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in the heart of stars that died in supernovae billions of years ago. You are quite literally made of stardust. But what about the core? What happens to that incredibly dense, compressed remnant at the heart of the explosion? For some stars, the core becomes a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain. But for the most massive stars, even the neutrons cannot withstand the crushing force of gravity. The collapse continues. The core compresses beyond the neutron star stage, beyond any known form of matter. It compresses until it becomes a mathematical point of infinite density, what we call a singularity. And around that singularity, space-time warps so severely that it creates a boundary, a surface beyond which nothing can return. This boundary is the event horizon, and together, the singularity and its event horizon form what we call a black hole. It is important to pause and appreciate the sheer extremity of what we are describing. A black hole is not made of any conventional material. It is not made of atoms or molecules or even subatomic particles in any recognizable sense. It is a region of spacetime so warped that it has essentially cut itself off from the rest of the universe. Inside the event horizon, spacetime is curved in such a way that all paths, every possible trajectory, lead inexorably toward the singularity at the center. To be inside a black hole is to be in a place where moving away from the center is as impossible as traveling backward in time. And yet, from the outside, a black hole appears surprisingly simple. It is defined by just a few properties: its mass, its spin, and if it is electrically charged, its charge. Everything else about the star that created it, its composition, its history, its complexity, all of that information is lost forever behind the event horizon. Physicists sometimes say that black holes have no hair, meaning they have no distinguishing features beyond these basic properties. It is a strange kind of simplicity born from the most extreme complexity. As we prepare to approach our black hole, let this paradox settle in your mind. The most complex object imaginable, reduced to elegant mathematical simplicity. Our spacecraft begins its journey from a safe distance, perhaps a few light years away from our destination black hole. At this distance, the black hole is merely a dark patch against the stellar background, notable mainly for the way it seems to bend and distort the light of stars behind it. This gravitational lensing effect is our first real glimpse of the power we are approaching. The black hole we have chosen for our journey is neither the smallest nor the largest known. It has a mass roughly 10 times that of our Sun, collapsed into a region smaller than a city. The event horizon, our ultimate destination, has a radius of about 30 kilometers. As we begin our approach, you might expect to see the black hole grow larger in our viewport. And indeed it does, but not in the way you might imagine. The gravitational lensing effect becomes more pronounced with every kilometer we travel closer. Stars that should be behind the black hole appear above it, below it, to the sides. Some stars appear in multiple locations, their light bent around the black hole in different paths. It is as if we are looking through a cosmic funhouse mirror, except this mirror is not made of glass and silver, but of warped spacetime itself. Let us take our time on this approach. There is no need to rush toward the event horizon. Part of the beauty of this journey is in the gradual revelation of the black hole's effects on the space around it. We are not just traveling through space. We are traveling through increasingly curved spacetime, and the laws of physics we take for granted are beginning to shift in subtle but profound ways. Even here, still far from the event horizon itself, time is running slightly slower for us than it would for someone remaining at a safe distance. The difference is tiny, imperceptible to our senses, but it is real and measurable. This is one of the most remarkable predictions of Einstein's theory of general relativity, confirmed countless times through observation and experiment. Gravity does not just bend space. It bends time as well. The stronger the gravitational field, the slower time passes. On Earth, time runs slightly slower at sea level than it does on a mountain top. The difference is minuscule, measured in nanoseconds, but it is there, and it must be accounted for in the global positioning system satellites that orbit our planet. Near a black hole, however, this effect becomes dramatic, impossible to ignore, world-changing in its implications. As we continue our approach, moving ever closer to the event horizon, this time dilation effect will grow stronger and stronger. Eventually, it will dominate our experience in ways both beautiful and unsettling. But we are not there yet. For now, we are still in what we might call the outer reaches of the black hole's influence, where its presence is felt but not overwhelming. This is a good place to pause, to observe, to let the reality of what we are seeing truly sink in. We are approaching a tier in the fabric of spacetime itself, and we are doing so peacefully, contemplatively, with wonder rather than fear. You might wonder what we hope to find on this journey. What knowledge, what insight, what revelation awaits us at the event horizon? The truth is, the journey itself is the revelation. By approaching the event horizon, we are not just learning about black holes. We are learning about the fundamental nature of space and time, about the limits of physics, about the questions that lie at the very heart of our understanding of reality. Some of the greatest mysteries in physics involve what happens at the event horizon and beyond. Does information that falls into a black hole truly disappear forever? How do quantum mechanics and gravity reconcile in such extreme conditions? These are not idle academic questions. They go to the heart of how our universe works at its most fundamental level. The event horizon is a place where our current theories reach their limits, where new physics must emerge to explain what we observe. And yet, despite the profound questions it raises, there is something deeply calming about contemplating the event horizon. It reminds us that the universe is larger, stranger, and more wonderful than our everyday experience suggests. It invites us to think beyond our usual concerns and to marvel at the cosmic dance of matter, energy, space, and time. As our spacecraft continues its gradual approach, let us take a moment to appreciate the privilege of this journey. We are exploring, through thought and imagination, a region of space that represents the extreme limit of what is possible under the laws of physics as we understand them. We are witnessing the universe at its most dramatic, its most unforgiving, and paradoxically, its most revealing. The event horizon awaits us ahead, a boundary that once seemed purely theoretical, but that we now know exists in reality throughout the cosmos. Our adventure is just beginning, and the most remarkable revelations are still to come. Now that we have been traveling for a while and the black hole has grown significantly in our viewport, it is time to ask a fundamental question. What exactly is the event horizon? The name itself gives us a clue. An event is something that happens, and a horizon is a boundary beyond which we cannot see. The event horizon, then, is quite literally the boundary beyond which events cannot be observed from the outside. It is the ultimate edge, the point of no return, the place where the escape velocity equals the speed of light itself. Let us take our time to truly understand what this means. Think about escape velocity for a moment. It is the speed you need to achieve to break free from a gravitational pull. On Earth, the escape velocity is about 11 kilometers per second. This is why rockets need such powerful engines to leave our planet and enter space. The Moon has a lower escape velocity because it is less massive. Jupiter has a much higher escape velocity because it is far more massive. The more massive an object and the smaller its radius, the higher its escape velocity becomes. Now, imagine compressing so much mass into such a small space that the escape velocity reaches the cosmic speed limit, the speed of light. This is what happens at the event horizon. At this precise boundary, the escape velocity is exactly equal to the speed of light. Inside this boundary, the escape velocity exceeds the speed of light. But nothing in the universe, according to our current understanding of physics, can travel faster than light. This means that anything that crosses the event horizon, whether it is matter, energy, or even light itself, can never escape. It is trapped forever. The event horizon is not made of any material. It is not a solid surface you could touch. It is simply the mathematical boundary where this condition is met, where escape becomes impossible. For our black hole, with 10 times the mass of the Sun, the event horizon has a radius of about 30 kilometers. This distance is called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who first calculated it in 1915, just months after Einstein published his theory of general relativity. Schwarzschild's solution showed that for any amount of mass, you could calculate a radius at which the escape velocity would equal the speed of light. Compress any mass within its Schwarzschild radius, and you create a black hole. Schwarzschild himself did not believe such objects could exist in nature, but the universe, as we now know, had other ideas. The Schwarzschild radius scales directly with mass. Double the mass, and you double the radius of the event horizon. This means that supermassive black holes at the centers of galaxies, with masses millions or billions of times that of the Sun, have correspondingly enormous event horizons. The supermassive black hole at the center of our own Milky Way galaxy, which has a mass about 4 million times that of the Sun, has an event horizon with a radius comparable to the orbit of Mercury around the Sun. These cosmic giants are so large that you could, in principle, cross the event horizon without even noticing at first, at least not from tidal forces alone. But regardless of size, the event horizon always represents the same fundamental boundary. It is the point beyond which causality, as we understand it, ceases to connect the interior to the exterior. An event that occurs inside the event horizon cannot send any information to the outside universe. No light, no signal, no message of any kind can escape. This is why black holes are black. Not because they are made of some dark material, but because light itself cannot escape from within the event horizon to reach our eyes or our telescopes. The black hole is not absorbing light in the way a black piece of paper absorbs light. It is trapping light in curved space-time. There is something profoundly philosophical about the event horizon. It represents an absolute limit to knowledge. No matter how advanced our technology becomes, no matter how sophisticated our theories grow, we can never directly observe what lies beyond the event horizon. Any probe we send across that boundary will be lost to us forever, unable to transmit back what it finds. In a universe that often seems knowable given enough time and effort, the event horizon reminds us that some boundaries are truly absolute. And perhaps there is a strange peace in accepting that some mysteries will remain mysteries, some questions will remain unanswered. As we continue our approach and the event horizon grows ever larger in our view, filling more and more of the sky ahead of us, take a moment to contemplate this boundary. It is not sinister or malevolent. It is simply a consequence of the laws of physics taken to their logical extreme. The event horizon is as natural as the orbit of a planet or the fusion in a star's core. It is a part of the cosmic order, a feature of the universe we inhabit. Understanding it, contemplating it, even finding peace in its existence is part of what makes us human, part of our endless curiosity about the cosmos we call home. As we draw nearer to the event horizon, we must turn our attention to one of the most remarkable and counterintuitive effects of extreme gravity. Time itself begins to change. Not just metaphorically, but literally, measurably, profoundly. This phenomenon is called gravitational time dilation, and it is one of the most beautiful and strange predictions of Einstein's general relativity. To an outside observer watching our spacecraft approach the black hole, we appear to be moving slower and slower as we get closer to the event horizon. Not because our engines are failing or because we are losing speed, but because time itself is running slower for us relative to that distant observer. This is not an illusion or a trick of perception. Time genuinely passes at different rates in different gravitational fields. The stronger the gravity, the slower time flows. Near the event horizon of a black hole, this effect becomes extreme. If you were to hover just above the event horizon and look back at the universe, you would see the cosmos around you speeding up. Stars would be born, live their lives, and die in what seems like fast forward. Galaxies would evolve and change. Meanwhile, to an observer far from the black hole watching you, you would appear almost frozen, your movements slowed to an imperceptible crawl as you approached the horizon. Let us pause and really absorb this concept, because it challenges our everyday understanding of time as a universal constant. We are used to thinking of time as something that flows the same for everyone, everywhere. 1 second is 1 second, whether you are on Earth, on Mars, or in a distant galaxy. But general relativity tells us this is not true. Time is relative. It depends on where you are and how fast you are moving. Near a black hole, this relativity of time becomes impossible to ignore. The black hole does not just warp space. It warps the very fabric of space-time, the unified entity that encompasses both space and time. Imagine sending a light signal from our spacecraft back to a distant observer. As we get closer to the event horizon, that signal takes longer and longer to climb out of the gravitational well. The light is redshifted, stretched to longer wavelengths, losing energy in its struggle against gravity. If we could somehow hover at the event horizon itself, which is impossible without infinite energy, any light we emitted would take an infinite amount of time to reach the distant observer. From their perspective, we would appear frozen at the horizon, our image growing dimmer and redder, asymptotically approaching but never quite reaching the boundary. We would become a ghost, fading slowly into the darkness. But from our own perspective, aboard the spacecraft, something very different happens. To us, time seems to flow normally. We would not feel time slowing down. Our heartbeats, our thoughts, our perceptions would all seem unchanged. This is the essence of relativity. There is no absolute reference frame for time. Each observer has their own experience of time, and both experiences are equally valid. As we approach the event horizon, we would, from our own perspective, reach it and cross it in a finite amount of time. But to that distant observer, we would appear to take forever to get there, slowly fading from view without ever quite crossing the boundary. This difference in perspectives leads to one of the most profound paradoxes associated with black holes. From the outside, nothing ever actually crosses the event horizon. Matter and light approach it, slow down, freeze, and fade. The event horizon accumulates a historical record of everything that has ever fallen toward it, preserved forever in an increasingly redshifted, time-dilated state. Yet from the perspective of an object falling into the black hole, the crossing is inevitable and occurs in finite time. Both perspectives are correct within their own frames of reference. The universe contains multiple simultaneous truths, depending on your point of view. There is something deeply meditative about this realization. Time, which seems so absolute and unchanging in our daily lives, is revealed to be flexible, relative, dependent on context. The event horizon teaches us that our intuitions, built from our limited experience in weak gravitational fields, can mislead us when we venture into more extreme environments. It invites us to question our assumptions, to remain open to possibilities that seem to contradict common sense. And in doing so, it offers us a more complete, more accurate, and ultimately more wonderful understanding of the universe. The flow of time near a black hole is not an error in our theories. It is a feature of reality itself. As we continue our journey ever closer to the event horizon, keep this time dilation in mind. It will color everything we experience from here forward. The closer we get, the more pronounced the effect becomes. At distances of a few times the event horizon radius, the effect is noticeable but not overwhelming. At the event horizon itself, time dilation becomes infinite from an outside perspective. This is not science fiction. This is not speculation. This is the reality of spacetime near a black hole, supported by mathematics, by theory, and by observation. It is strange, yes. Counterintuitive, certainly. But it is also real, and it is magnificent. If time can be warped by gravity, what about light itself? Light, after all, is the fastest thing in the universe, the cosmic speed limit, the one constant we have in relativity. Surely light is immune to the distorting effects of space-time curvature. And yet, this is not the case. Light, despite its speed, despite its lack of mass, follows the curves in spacetime just like everything else. Near a black hole, these curves become so extreme that light's path is bent in spectacular and beautiful ways. This gravitational lensing effect is not just a curiosity. It is a powerful tool that has allowed astronomers to detect and study black holes that would otherwise be invisible. Imagine you are shining a flashlight near a black hole. If you aim the light directly at the black hole, it will be captured and disappear beyond the event horizon, never to return. But what if you aim the light just slightly to the side? The light will still be affected by the black hole's gravity. Its path will curve toward the black hole as it passes. If you aim it at just the right angle, the light will curve around the black hole and potentially come back toward you, having completed a partial orbit. This is light not traveling in a straight line, but following the curved geometry of spacetime itself. As we approach closer to the event horizon, this bending of light creates increasingly dramatic visual effects. Stars that are actually behind the black hole appear to be displaced, visible as a ring around it. This is called an Einstein ring, named in honor of the physicist whose theory predicted it. The ring is composed of light from stars and galaxies behind the black hole that has been bent around it to reach our eyes. In a perfectly symmetric situation, with the black hole, a distant star, and our spacecraft all perfectly aligned, we would see the star as a complete, perfect circle of light surrounding the black hole's darkness. But perfect alignment is rare, so more commonly we see partial arcs and distorted images. A single star might appear in multiple locations around the black hole, its light taking different paths around the gravitational lens to reach us. Some images might be stretched into long arcs. Others might appear brighter than they should be, magnified by the lensing effect. Looking at the space around a black hole is like looking through a cosmic kaleidoscope, where light paths twist and cross in ways that create a complex, ever-changing pattern. The view is both beautiful and disorienting, a reminder that even light, our primary means of observing the universe, can be dramatically altered by gravity. One of the most striking features we observe as we get very close to the event horizon is the increasingly bright ring of light that surrounds it. This is not the event horizon itself glowing. The event horizon emits nothing. Rather, this is light from the surrounding universe that has been bent so severely by the black hole's gravity that it appears concentrated into a bright ring. Light from stars in every direction is focused toward us by the gravitational lens. The effect is that the black hole appears surrounded by a luminous halo, bright against the darkness of its event horizon. This photon ring, as it is called, is a signature feature of black holes. The photon ring has a precise location, at exactly 1.5 times the Schwarzschild radius, or 1.5 times the radius of the event horizon. At this distance, spacetime is so curved that light can actually orbit the black hole. Photons traveling at just the right trajectory will circle the black hole in an unstable orbit, neither falling in nor escaping. Of course, this orbit is unstable. The slightest perturbation will cause the photon to either spiral inward, across the event horizon, or scatter outward into space. But theoretically, this photon sphere represents a location where light can orbit indefinitely, a luminous shell of circling photons surrounding the event horizon. From our vantage point near the black hole, we can witness these light-bending effects in real time. As we change our position, the patterns of bent starlight shift and change. The Einstein ring grows and shrinks. Multiple images of stars appear and disappear. It is a dynamic, ever-changing display of gravitational optics. If the black hole is rotating, which most real black holes are, the lensing effects become even more complex, with different behaviors depending on whether light is traveling with or against the black hole's rotation. The spinning black hole drags spacetime around with it, adding another layer of complexity to the already intricate paths that light must follow. These light-bending effects are not just beautiful. They are also scientifically invaluable. The first image of a black hole, captured by the Event Horizon Telescope in 2019, showed exactly these features. The bright ring surrounding the dark shadow of the event horizon. That image of the supermassive black hole at the center of the galaxy M87 confirmed decades of theoretical predictions and gave us our first direct visual evidence of an event horizon. As we hover here in our imaginary spacecraft, we are seeing with our own eyes, at least in our imagination, the same spectacular effects that radio telescopes have labored to capture. The universe, it turns out, is even more visually stunning than we dared to imagine. We find ourselves now at a special location, 1.5 times the radius of the event horizon from the black hole's center. This is the photon sphere, a region of such extreme spacetime curvature that light itself can orbit the black hole. It is an unstable equilibrium, a knife edge between falling inward and escaping outward. Photons traveling at precisely the right trajectory will circle the black hole at the speed of light, trapped in an eternal, precarious orbit. This is not a physical structure. Like the event horizon itself, the photon sphere is simply a mathematical boundary, a location defined by the geometry of curved spacetime. And yet, its effects are profound and observable. If you could somehow station yourself at the photon sphere and look around, you would see the most bizarre and wonderful sight. Looking inward, you would see the event horizon, that sphere of absolute blackness. Looking outward, you would see the rest of the universe, but grotesquely distorted by the extreme light bending. But most strangely of all, looking horizontally around the photon sphere, tangent to your orbit, you would see the back of your own head. Light leaving the back of your head would circle the black hole and return to your eyes from the front. You could, in principle, see yourself from every angle simultaneously, an infinite regression of images stretching around the curvature of space. Of course, maintaining a position at the photon sphere would require constant thrust, constant energy input. The gravitational pull here is intense. Any object with mass would need to fire its engines continuously, just to avoid falling toward the event horizon. Only light, traveling at the cosmic speed limit, can maintain this circular orbit without effort, and even then, only in a theoretical, perfectly balanced scenario. In reality, any light orbiting at the photon sphere is just one tiny perturbation away from either spiraling inward or scattering outward. It is a fleeting phenomenon, beautiful in its instability. The photon sphere plays an important role in the appearance of black holes. It is responsible for much of the bright ring we see surrounding the event horizon. Light from distant sources can become temporarily captured in quasi-stable orbits near the photon sphere, circling the black hole multiple times before either falling in or escaping. Each time the light circles, we might see it again from a slightly different angle. This creates a series of nested bright rings, each fainter than the last, stacked concentrically around the event horizon. The effect is subtle but measurable, a fingerprint of the photon sphere imprinted on the light we observe. For a rotating black hole, which is the more common case in nature, the photon sphere becomes even more interesting. The rotation of the black hole drags spacetime around with it, an effect called frame dragging. This means that light traveling in the same direction as the black hole's rotation can orbit at a slightly larger radius than light traveling against the rotation. The photon sphere splits into two surfaces, one for prograde orbits and one for retrograde orbits. The dragging of spacetime creates asymmetries in the light patterns, making the black hole appear brighter on one side than the other, even if the surrounding material is uniformly distributed. The concept of the photon sphere invites us to think about the nature of orbits in a new way. We are familiar with orbits from our experience in the solar system. Planets orbit the sun. Moons orbit planets. Satellites orbit Earth. But these are all material objects with mass, following curved spacetime at speeds far below the speed of light. The photon sphere shows us that even light, despite having no mass, despite traveling at the ultimate speed, still follows the curvature of spacetime. Light, in a sense, can orbit just like a planet or a moon. It is a profound reminder that gravity is not a force pulling on mass, but rather the shape of spacetime affecting everything that moves through it. As we prepare to venture even closer to the event horizon, let us take a moment to appreciate the photon sphere for what it represents. It is a location where the universe is balanced on a knife edge, where light teeters between escape and capture. It is a demonstration of the extreme curvature that is possible in spacetime, a preview of the even more extreme conditions we will encounter as we approach the horizon itself. The photon sphere is a place of exquisite mathematical beauty, where the equations of general relativity reveal surprising and counterintuitive behaviors. It reminds us that the universe operates according to rules that are often far stranger than our everyday experience suggests. From the photon sphere, the event horizon looms large and dark below us. The pull of gravity is intense, and maintaining our position requires significant energy. But we are not ready to cross that final boundary just yet. We are taking our time, observing, learning, appreciating the incredible physics at play in this extreme environment. The photon sphere is one of the last stable locations before the point of no return. It is a vantage point from which we can observe the event horizon in all its dark majesty, surrounded by the brilliant light it has captured and bent. Soon we will venture closer still, but for now we linger here, suspended between two cosmic extremes. The time has come to leave the relative safety of the photon sphere and venture closer to the event horizon itself. As we descend, the effects we have observed so far intensify dramatically. The time dilation becomes more extreme. The bending of light becomes more severe. The gravitational pull becomes overwhelming. Every kilometer we travel inward represents a step into increasingly alien physics, into conditions that exist nowhere else in the universe except near these cosmic extremes. This is the final approach, the last leg of our journey to the boundary of the knowable. Take a deep breath and prepare yourself for what we are about to witness. As we fall inward, we begin to experience tidal forces in a way that becomes impossible to ignore. Tidal forces arise because gravity decreases with distance. Your feet, being slightly closer to the black hole than your head, feel a slightly stronger gravitational pull. For Earth's gravity, this difference is negligible, barely noticeable. But near a black hole, these tidal forces can become extreme. For a stellar mass black hole like ours, these forces would grow strong enough to stretch and compress matter long before reaching the event horizon. This process has been colorfully termed spaghettification, and while violent, it is a natural consequence of the rapidly changing gravitational field. Fortunately, our journey is one of imagination and thought, so we can choose to observe these effects without experiencing them personally. As we continue our descent, the event horizon grows to dominate our entire forward view. It is no longer a circle ahead of us, but a vast dark wall, a hemisphere, then a sphere that seems to enclose us. The distortion of the surrounding star field becomes total. Stars that were above us now appear to be compressed into a shrinking circle directly behind us. All of the light from the external universe is focused into an increasingly small region of sky. Ahead and to the sides, there is only darkness, the absolute black of the event horizon. The light we do see is incredibly blue-shifted. Remember that light trying to climb out of a gravitational well loses energy and shifts toward red. Well, light falling into a gravitational well gains energy and shifts toward blue. As we fall inward, the light from the universe behind us becomes more and more energetic, shifting from visible light toward ultraviolet, then X-rays, then gamma rays. If this were a real physical journey, we would need extraordinary shielding to protect us from this increasingly energetic radiation. The universe itself becomes a deadly beacon as we approach the event horizon, all its light compressed and amplified by our fall through curved spacetime. From the perspective of an observer far from the black hole, something very different appears to be happening. Remember our discussion of time dilation. As we fall toward the event horizon, time slows down for us relative to that external observer. From their perspective, we are moving slower and slower, asymptotically approaching but never quite reaching the event horizon. Our image becomes increasingly redshifted and dim. We fade from view, gradually, over what would seem to them like an eternity. To them, we never cross the event horizon. We simply freeze at its edge and slowly vanish into the darkness, taking an infinite amount of their time to make that final infinitesimal approach. But from our perspective, from inside our falling reference frame, everything is very different. Time continues to pass normally for us. Our clocks tick at their regular rate. Our thoughts proceed at their usual pace. We do not feel time slowing down because, from our perspective, it is not. We are simply falling, accelerating under the influence of gravity, approaching a boundary that we will reach and cross in a finite, measurable amount of our time. The event horizon does not appear special to us from this perspective, at least not initially. It is not a wall or a barrier or a surface. It is simply a location in space that we are approaching and will soon pass. This dual perspective, this difference between what we experience and what an external observer sees, is one of the most profound aspects of relativity. There is no absolute truth about when or if we cross the event horizon. From outside, we never cross it. From inside our reference frame, we do cross it at a specific moment in our time. Both perspectives are valid within their own frames of reference. The universe does not have a single, objective timeline. Reality depends on where you are and how you are moving. This is not a limitation of our understanding. It is a fundamental property of spacetime itself, revealed most clearly in the extreme environment near a black hole. As we make this final approach, take a moment to reflect on how far we have come, both literally and intellectually. We began our journey from a safe distance, where the black hole was merely a dark spot against the stars. We have traveled through regions of increasing gravitational intensity, witnessing time dilation, light bending, the photon sphere, and now the immediate vicinity of the event horizon itself. We have explored physics at its most extreme, where our everyday intuitions fail, and only the mathematics of general relativity can guide us. And now we stand, or rather fall, at the threshold of the ultimate boundary. The event horizon awaits, just ahead, just below, inevitable and absolute. And now the moment has come. From our perspective, falling freely toward the black hole, the event horizon is not a dramatic barrier or a wall of fire. It is simply a location in space that we pass through. For a large enough black hole, like a supermassive one, you might not even notice the crossing at first. There would be no physical sensation, no bump or jolt or change. The tidal forces, while growing, might still be survivable at the horizon of a very large black hole. One moment you are outside the event horizon, still theoretically able to escape if you had infinite energy. The next moment you have crossed it, and escape has become impossible. The transition is smooth, seamless, inexorable. What has changed? From a certain perspective, everything, and from another perspective, nothing at all. The laws of physics have not changed. Light still travels at the speed of light. Time still flows. Gravity still pulls. But the geometry of spacetime has changed in a fundamental way. Inside the event horizon, all paths through spacetime, every possible trajectory, every geodesic, leads inward toward the singularity. It is not that you are being pulled toward the center by some irresistible force, though it may feel that way. It is that the very structure of spacetime inside the horizon is such that moving toward the singularity is as inevitable as moving forward in time. Outside the event horizon, time is a dimension separate from the three dimensions of space. You can move forward and backward in space, but you can only move forward in time. Inside the event horizon, this relationship fundamentally changes. The radial direction toward the singularity becomes time-like, while time becomes space-like. This is difficult to visualize because it is so far removed from our experience, but the implication is profound. Inside the event horizon, moving toward the singularity is as inevitable as the passage of time itself. Reaching the singularity is not just likely or probable. It is absolutely certain, guaranteed by the structure of spacetime itself. You might wonder what we would see after crossing the event horizon. The view would continue to be dominated by the external universe, compressed into that bright circle behind us, growing smaller and smaller, but never disappearing entirely. We could still see the outside universe, receiving light that falls in after us. In principle, we could watch the rest of cosmic history unfold in fast forward, as the time dilation effect works in our favor. Stars would live and die. Galaxies would evolve. The universe would age. All of this we could observe, at least until the tidal forces or other effects ended our ability to observe anything. But we could never send any information back. We could watch, but we could not communicate. The event horizon, is a one-way membrane in space-time. Information can pass inward through it, but never outward. This has led to deep questions in theoretical physics about the nature of information and the foundations of quantum mechanics. If information that falls into a black hole is truly lost forever, this seems to violate quantum mechanics, which requires that information be preserved. This puzzle, known as the black hole information paradox, has occupied physicists for decades and remains one of the deepest unsolved problems in theoretical physics. The event horizon, this smooth, seamless boundary, holds secrets that challenge our most fundamental understanding of nature. Some theories suggest that the event horizon is not as smooth and empty as classical general relativity suggests. Quantum effects near the horizon might create what has been called a firewall, a region of intense energy that would destroy anything trying to cross. Other theories propose that information is somehow encoded on the event horizon itself, in a holographic manner, allowing it to be preserved even as matter falls inward. These ideas remain speculative at the cutting edge of theoretical physics. Attempts to reconcile general relativity with quantum mechanics in the most extreme environment imaginable. The event horizon is not just a boundary in space. It is a boundary in our knowledge, a place where our current theories reach their limits. As we continue our journey inward, now irreversibly committed to reaching the singularity, we might feel a range of emotions. Fear, perhaps, at the inevitability of what is to come. Wonder, certainly, at the incredible physics we are experiencing. Peace, maybe, in accepting the absolute certainty of our trajectory. There is something almost meditative about the inescapability of the singularity once we have crossed the event horizon. All choices have been made. All possibilities have collapsed to one. We are now simply along for the ride, observers of the final stages of our journey into the unknown. In surrendering control, we might find a strange freedom, a release from the burden of choice. The crossing of the event horizon is perhaps the most significant moment in our journey, even if it is not marked by any dramatic physical change. It is the point where we have truly entered the black hole, where we have passed from the universe as we know it into a region that is, in some sense, separate from the rest of spacetime. We are now inside, committed, bound for the singularity. What awaits us there is the final mystery, the ultimate unknown. But before we confront that mystery, let us appreciate what we have experienced. We have witnessed the point of no return, not as a barrier or a surface, but as a smooth, inevitable transition written into the geometry of the universe itself. Inside the event horizon, our journey continues, but now with an absolute destination. The singularity at the center of the black hole awaits us, and nothing we can do will prevent us from reaching it. The tidal forces, which have been growing throughout our journey, now begin to dominate our experience. For a stellar mass black hole like ours, these forces would have already become lethal, stretching matter into long, thin filaments. But in our thought experiment, we can observe these effects from a protected perspective. The differential gravitational pull between different parts of space grows, without bound, as we approach the singularity. Spacetime is not just curved here. It is being stretched toward infinite curvature. The singularity itself is one of the deepest mysteries in physics. According to general relativity, it is a point of infinite density and zero volume, where all the mass that has fallen into the black hole is compressed into an infinitesimal space. At the singularity, the curvature of spacetime becomes infinite, and the equations of general relativity break down completely. They produce infinities, which in physics is usually a sign that the theory has reached its limits. The singularity is not really a place in the usual sense. It is more like a moment in time, an endpoint beyond which spacetime itself ceases to be defined. What happens there? Honestly, we do not know. Most physicists believe that the singularity, as predicted by general relativity, is not truly physical. It is a placeholder, a signpost indicating where our current theory fails and a new theory is needed. That new theory would be a quantum theory of gravity, a framework that successfully merges quantum mechanics with general relativity. String theory, loop quantum gravity, and other approaches attempt to provide such a framework, and many of them predict that the singularity is resolved at the quantum level. Perhaps instead of a point of infinite density, there is some kind of quantum bounce or a region of extremely high but finite density. The true nature of the singularity remains an open question at the frontier of physics. What we can say with confidence is that the singularity represents the end of our journey. Once we reach it, our path through spacetime comes to an end. There is no beyond the singularity in the usual sense. Spacetime itself terminates there. It is an endpoint, a boundary not in space but in time. For anyone who crosses the event horizon, reaching the singularity is not just probable or likely. It is absolutely certain, written into the causal structure of spacetime inside the horizon. The time from crossing the event horizon to reaching the singularity depends on the mass of the black hole. But for a stellar mass black hole, it would be a fraction of a second. There is something profound, almost spiritual, about contemplating the singularity. It represents the absolute limit of the physical world as we understand it. Beyond the singularity, there is no space, no time, no structure. It is not just unknown. It is, in a sense, unknowable within our current framework. And yet, the universe permits these objects to exist. Black holes are not rare curiosities. They are common throughout the cosmos, the inevitable endpoint of massive stars. The universe is filled with these boundaries, these limits, these regions where the familiar gives way to the utterly alien. In contemplating them, we are contemplating the edges of reality itself. For our purposes, this is as far as our journey can take us. We have traveled from a safe distance, through regions of increasing spacetime curvature, across the event horizon, and approached the singularity itself. We have witnessed time dilation, gravitational lensing, the photon sphere, and the point of no return. We have contemplated the deepest mysteries in physics and come face to face with the limits of our understanding. The singularity remains shrouded in mystery, but our journey to reach it has been filled with wonder, beauty, and profound insight into the nature of the cosmos. It is time now to step back, to reflect, to emerge from this thought experiment and return to our everyday world. Of course, in physical reality, there is no coming back from inside a black hole. The event horizon is truly one way. But in the realm of imagination and thought, we can extract ourselves, bringing with us the knowledge and perspective we have gained. We have seen the universe at its most extreme, experienced physics at its limits, and confronted the boundaries of space and time themselves. This journey, while theoretical, is grounded in real mathematics and real physics. The time dilation, the light bending, the event horizon, the singularity, these are not fantasies. They are features of our universe, predicted by our most successful theories and confirmed by observation. They are real, even if they are strange. As we leave the singularity behind, unvisited but acknowledged, let us carry with us the lessons of this journey. We have learned that the universe is far stranger than our everyday experience suggests. We have learned that space and time are not the fixed, absolute stage we once thought, but dynamic, flexible, and intimately connected. We have learned that there are boundaries to knowledge, places where our current understanding reaches its limits. And we have learned that these limits, far from being frustrating, are invitations to deeper inquiry, to new theories, to expanded understanding. The singularity awaits future physicists, armed with new tools and new insights. For now, we honor its mystery. Our journey through the physics of black holes and event horizons has been intense, filled with challenging concepts and counterintuitive truths. But underlying all of it has been an opportunity for something more personal, more meditative. The event horizon, in all its absoluteness and mystery, offers us a unique mirror for contemplation. It reminds us of the boundaries we face in our own lives, the points beyond which we cannot return, the decisions that, once made, commit us to a particular path. In understanding the physics of black holes, we might also gain insight into the nature of commitment, inevitability, and acceptance in our own experience. There is something deeply meditative about contemplating the event horizon. It is a boundary that is absolute, unchanging, and yet invisible from the inside. It teaches us about the nature of thresholds, about the moments in life when we pass from one state to another, often without immediately recognizing the transition. How many event horizons have we crossed in our own lives? Moments where, looking back, we realize that a particular choice or circumstance committed us to a path, even though at the time it seemed like just another step. The event horizon invites us to reflect on these personal boundaries, these points of no return that shape our journey through life. The inevitability of the singularity, once the event horizon is crossed, can be seen as a metaphor for the way we move through time. We cannot stop time. We cannot reverse it. We can only move forward, moment by moment, toward an unknown future. Inside the event horizon, moving toward the singularity is as inevitable as the passage of time itself. In our lives, aging, change, and eventual death are similarly inevitable. Rather than causing despair, this recognition can bring peace. There is freedom in accepting what cannot be changed, in surrendering to the flow of time and making the most of each moment we have. The event horizon teaches us acceptance. The relativity of time near a black hole reminds us that our experience of reality is deeply personal and subjective. What seems fast to one person may seem slow to another. A moment that feels eternal to you might pass in a flash for someone else. This relativity extends beyond just time perception. Our emotions, our priorities, our sense of what is important, all of these are relative, shaped by our position in life, our experiences, our personal trajectory. The black hole teaches us that there is no single, absolute perspective. Every viewpoint is valid within its own frame of reference. This can cultivate compassion and understanding for others, whose experience differs from our own. The event horizon also teaches us about information and communication. Once inside the event horizon, you can still receive information from the outside universe, but you cannot send any information back. This one-way flow of information is, in a sense, like the flow of time. We can receive information about the past. We can remember and reflect on what came before, but we cannot send information backward in time. We cannot change what has already happened. All we can do is move forward, taking the lessons of the past with us, using them to inform our choices in the present moment. The event horizon is a reminder to focus on what we can influence, which is only ever the present moment. The singularity, that point of ultimate mystery at the heart of the black hole, reminds us that there are things we cannot know, limits to understanding that may be fundamental rather than just temporary. In an age that often promises complete knowledge and total information, the singularity is a humbling reminder that mystery is a permanent feature of existence. There will always be questions without answers, phenomena beyond our comprehension, aspects of reality that remain stubbornly mysterious. Rather than being a source of frustration, this can be liberating. We are not required to understand everything. It is acceptable, even healthy, to live with uncertainty and mystery. The singularity teaches us humility. Throughout our journey, we have seen beauty in the extreme, wonder in the mathematical, and peace in the cosmic. The event horizon, for all its strangeness and intensity, is fundamentally a natural phenomenon, as much a part of the universe as a sunset or a rainfall or the orbit of the moon. It follows natural laws, obeys mathematical equations, exists as part of the cosmic order. In contemplating it, we are reminded that we too are part of this cosmic order. The same laws of physics that govern the black hole govern the atoms in our bodies. We are made of the same stuff as stars. We follow the same fundamental rules. We are not separate from the universe. We are the universe experiencing itself, contemplating its own nature. As our meditation on the event horizon comes to a close, take a few deep breaths. Feel the air entering your lungs, oxygen molecules that were once part of a distant star. Feel the ground beneath you, atoms that have journeyed through billions of years of cosmic history to be here now, supporting you in this moment. You are a temporary gathering of stardust, conscious and aware, capable of contemplating the deepest mysteries of existence. The event horizon, that ultimate boundary in spacetime, exists out there in the cosmos, and yet its lessons apply here, now, in your life. You have boundaries, thresholds, inevitabilities, and mysteries of your own. May the peace and wonder we found in contemplating the cosmos bring you tranquility in your own journey. Our journey to the event horizon is complete. We have traveled from the familiar realm of everyday physics to the extreme boundary where spacetime itself is pushed to its limits. We have witnessed time dilation, gravitational lensing, the photon sphere, and the point of no return. We have contemplated the singularity and found, in the physics of black holes, reflections on the nature of life, time, inevitability, and mystery. The event horizon remains out there in the cosmos, silent and absolute, a feature of our universe that will endure long after we are gone. Thank you for taking this journey with me. May the wonder of the cosmos bring you peace, and may you carry the lessons of the event horizon with you as you navigate the boundaries and thresholds of your own life. Until we meet again under these cosmic skies, stay curious, stay peaceful, and never stop looking up.